Hello friends, in this session we will see how to find the solution to state space equations by using Cayley-Hamilton method. Let's begin. So now before starting with the exact Cayley-Hamilton method, let us first understand what is the Cayley-Hamilton theorem. What does the theorem say? Let us see that. Cayley-Hamilton theorem states that every square matrix satisfies its own characteristic equation, right? Now see here, what do we mean by satisfying its own characteristic equation? It means that, for example, if you have some characteristic equation, right, and we know that always a characteristic equation, it is in terms of lambda, right? It is in terms of lambda, maybe probably lambda squared, or something sort of like that, right? So what does this mean? This means that every square matrix, let me call that I have a square matrix A, for example. Then square matrix A satisfies its own characteristic equation means that I can replace this lambda by A. Let me write it in another color. I can replace lambda by A. This is what the theorem states. Now there is another thing with it. What is that thing? See here. This is the theorem. We have understood the theorem. What does that say? That whatever characteristic equation, if you see yes, we say that determinant of Si minus A equal to 0 is nothing but the, what do you say, is nothing but the characteristic equation, right? Characteristic equation. So here if you see, all the expression that we will get, that will be in terms of s squared, s cube, and something like that, right? So there if you see, now we know that this s which is there, that equated to 0, that will give you the poles. And in linear algebra we say the same things as eigenvalues. So basically, let me just recall that the poles here are also called as eigenvalues, which means this s here can be replaced by lambda as well. And what do we mean by this lambda? Lambda is nothing but the eigenvalues. We have seen that, right? Lambda is nothing but the eigenvalues. So basically that eigenvalue lambda can be replaced by A. That is what is the first theorem. Another thing, it states that this particular matrix A which is there, that can be written as a function of A in this particular manner. What is that? F of A is equal to alpha naught I plus alpha 1 A plus alpha 2 A squared, and this just goes on up to alpha n A to the power n minus 1. This expression is very, very important. What does it mean? It means that for any matrix A, if you apply some function, let us say you have some matrix A, right? You apply a function on it, right? Then whatever you get, that can be represented, that particular function of A can be represented in this particular manner. This is very, very important. Please make a note of this, right? Now let us involve this with our state space. We will firstly write down the steps, and then we will start with the procedure, right? Yes. So now steps to be followed. What are the steps which we have to follow? The first step is, yes, definitely. The first step is to find eigenvalues of A. Then the next step is what? You need to express, because you see here this particular f of A. Why? We need to understand that, when we are talking about state transition matrix STM, what is that matrix? That is nothing but e to the power 80, right? which means if you have matrix A, then you are applying some function to this A, and that function is nothing but e raised to at. Am I right? Yes. So see, basically I want to say that keep things very simple. If you just see here, you have this alpha naught. What is alpha naught? What is alpha 1? What is alpha 2? They are nothing but constants. No problem. What is this n? This n means order of the system, right? And this a is what? A is the system matrix, and this I is the identity matrix, right? We all know that. Now let us do that, because see, this particular expression is going to be very important. Why it is important, you will come to know in a while. Okay. Yes. Now the first step was to find the eigenvalues. The next step is to express in terms of e to the power lambda t, because see, I just told you that f of a can be written as e to the power at, and we know that this a can be replaced by lambda. That is what we were talking about, right? Cayley-Hamilton theorem. So basically the first thing which we have to do is you just need to replace it as e to the power lambda t, which is equal to alpha naught plus alpha 1 lambda plus this goes on up to alpha n lambda n minus 1. That is what we can write. Means you need to express a in terms of this one, e to the power lambda t, right? Now see, do you have the values of eigenvalues? Yes. The moment you have eigenvalues, now see here, eigenvalues will be definitely either it can be one also, but then for time example, if you consider second order system, then there will be two eigenvalues, right? Two eigenvalues. Similarly, if you think of third order system, then definitely there will be three eigenvalues, right? So in such a case, what are you supposed to do? You please replace, you please substitute. That is what is the step 3. Step 3 says that you please substitute all those possible values of lambda, all those lambdas means eigenvalues, all those eigenvalues, right, in this particular equation which you have got in the step 2, and and try to find the values of alpha naught, alpha 1, and so on. Now what does this mean? You will understand it in a short period of time. You just don't worry about it. It is a very simple concept. Keep things very simple. Don't complicate. Anyways, the fourth step that we have to follow is, the fourth step is nothing but use the values of alpha naught, alpha 1, alpha 2, and what do you do? Replace this lambda which is there in the second step, this lambda which is there in second step, by a, right? Such that you will get e to the power at. Now how does it happen? I will tell you, don't worry. We will just get into the example, get into the original stuff. Yes, see here, let me take the first example, because we know that yes, e raised to at is what? E raised to at is nothing but state transition matrix. After that you need to only find the output is nothing but what? C into x of t. That is what we know. It's perfectly fine, no problem. Now let us try to find the STM, right? So let us take some example. Yes, so now here they are asking you to find the state transition matrix STM for a state space equation using Cayley-Hamilton theorem. Basically, see, this question will never be asked in GATE. Such question will never be asked in GATE, right? But you should know that how the steps have to be used. That's it, right? Anyways, so if you think of step 1, step 1 is what? To find eigenvalues, right? To find eigenvalues of A. How to do that? How to do that eigenvalues? Yes, we know that it is nothing but determinant of Si minus A equal to 0. That is what we know. Now, how to find that Si minus A? Just simply do this. See, if you want to find Si minus A, what is Si minus A? It is equal to, you need to have this S into I, right? Which is nothing but S0, 0, S. We have already seen this. Then you have got this minus sign into A. What is A? Yes, A is 0, 1, minus 2, minus 3, which is given. Am I right? Yes. Now, what do? You will just simply subtract. So this S minus 0 is nothing but S. 0 minus 1 is going to be minus 1. 0 minus of minus 2 is going to be plus 2. And S minus of minus 3 is going to be S plus 3. Right? This is nothing but Si minus A. Right? Now you need to find the determinants and equate it to 0. So if you find the determinant of this, what do you get then? Determinant is nothing but this into this minus this into this. Right? So let me just take the determinant. So determinant of Si minus A is going to be what? S into S plus 3 minus 2 into minus of 1. 2 into minus of 1. So this becomes S squared plus 3S plus 2. Is that correct? Yes. Now if I try to factorize it, I will get that the roots are S equal to, what do you say, minus 1 and S equal to minus 2. Right. This is the basic 10th standard mathematics. You should be knowing this mathematics. In case if you don't know, let me just explain. See, what have they given? Do you agree that it is a quadratic equation? Quadratic equation, yes, definitely. Now you please take this term, the last term, right? It is 2. Is it positive 2? Yes, it is positive 2. So you please find two numbers. You please find two numbers such a way that their multiplication will be 2. Their multiplication will be 2 and their sum will be plus 3. So let us find them. Those are going to be 2 and 1 because we know that 2 multiplied with 1 will give you 2 and 2 plus 1 will give you 3. So it is nothing but, yes, so now you have to represent it in terms of S plus 2 and S plus 1. These are the two factors. Now the moment I equate them to 0, what happens is S plus 2 equated to 0, we get S equal to minus 2, and S plus 1 equal to 0, we get S equal to minus 1. Is that correct? Yes. Now, so now if you just see here, you may say that, sir, but these are the poles, right? S equal to minus 1, S equal to minus 2. Yes, these are the poles. But we have already seen that the poles are nothing but the eigenvalues only. So I can now call these poles as eigenvalues also. So these are nothing but basically lambda 1 equal to minus 1 and lambda 2 equal to minus 2. Is that right? Now, see, yes. So now what is the step 2? Step 2 is what? Express it in terms of e to the power lambda t. So that is the step 2. Step 2 is what? Express in terms of e to the power lambda t. Now if you see, we have only second order system, right? This particular system which is given, it is a second order system. So I will be having alpha naught plus alpha 1 into lambda. Why? There will be only two constants. Why? Because it is a second order system. And another thing is that you have two eigenvalues, right? So now what will I do next is I will first put lambda equal to minus 1. Lambda equal to minus 1. The moment I put lambda equal to minus 1, what do I get is e to the power minus 1t, which is nothing but alpha naught plus alpha 1 into lambda. Alpha 1 into lambda is minus 1. So I get e to the power minus t is equal to alpha naught minus alpha 1. That is the first equation I have got. Now, what will I do next? I will put the another eigenvalue. So it becomes put lambda equal to another eigenvalue is minus 2. So let me just replace that. So put lambda equal to minus 2. After replacing minus 2, what do I get here is e to the power minus 2t, because see, in this equation we are putting, right? So in place of lambda, if you put minus 2, you will get e to the power minus 2t, which is equal to alpha naught plus alpha 1 into lambda is nothing but minus 2. So then yes, it is going to be, therefore e to the power minus 2t is equal to alpha naught minus 2 times alpha 1. I hope this is clear, right? So yes, definitely. Rather, what can I do is I can say that this equation is 1, this equation as 2, and I can call this equation as 3. It is okay, it is completely your choice. So now if you see, you have got two equations, right? This is one equation, this is another equation, and you have got two unknowns as well. What are unknowns? Are nothing but alpha naught and alpha 1. So now let us find them. How to find the unknowns? See, how to find this? Very simple. Let me just subtract. If I subtract 2 and 3, what do I get? This alpha naught and alpha naught will get cancelled, right? Let me just do that. So if I do, let us say 2 minus 3, equation 2 minus equation 3, what do I get then? I get this e to the power minus t, which is equal to alpha naught minus alpha 1, minus, yes, what is that? E to the power minus 2t, which is equal to alpha naught minus 2 times alpha 1. As usual, we know that we just change the signs here. In our school days we have seen. So after that, what do you get here is, yes, you get e to the power minus t minus e to the power minus 2t, which is nothing but equal to alpha naught is cancelled, and you get here minus alpha 1 plus 2 times alpha 1. What does this mean? It means that e to the power minus t minus e to the power minus 2t is nothing but equal to minus alpha 1 plus alpha 2 is nothing but what? Alpha 1. So you have got the value of alpha 1 now. E to the power minus t minus e to the power minus 2t is nothing but your alpha 1. So let me call this as 4. Is that correct? Yes. Now, let me think of another one. What is that? See, if I think of, so alpha 1 is there, right? Yes. Now, if I just replace this, put this 4 into, if I replace this 4 into, what do I get? What is 2 actually? 2 is nothing but e to the power minus t is equal to alpha naught minus alpha 1. Right? Value of alpha 1 is already there. So if I just replace this value of alpha 1 here, what will I get? I get alpha naught minus alpha 1. Alpha 1 is nothing but e to the power minus t minus e to the power minus 2t. And this is e to the power minus t. Therefore, what you get is alpha naught equal to e to the power minus t. And this all goes there. So plus e to the power minus t. Right? Plus e to the power minus 2t. Therefore, what is alpha naught here? Alpha naught is going to be, if you just see here, these two terms will get added. So it is going to be 2 times e to the power minus t plus e to the power minus 2t. Is that correct? Yes. Let me call this as equation 5. So now you have got the values of alpha 1 and alpha 2. Now you just simply replace those in this equation 1. In this equation 1. So put 4 comma 5 in 1. Very simple. So if you just replace them in 1, what do you get there? E to the power lambda t is nothing but equal to alpha naught. What is alpha naught? 2 times e to the power minus t plus e to the power minus 2t plus, what is next? Alpha 1 into lambda. What is alpha 1? Alpha 1 is nothing but e to the power minus t minus e to the power minus 2t into lambda. Right. This is what is the expression. Right. Now, just use the Cayley-Hamilton theorem. What does the theorem say? Theorem says that the characteristic equation, every square matrix satisfies its own characteristic equation. So, you please replace lambda by a. The moment you replace it, what do you get? You get, see, this is lambda. So, you please put here a. So, it gets e to the power at, which is nothing but 2 times e to the power minus t minus e to the power minus 2t plus e to the power minus t minus e to the power minus 2t into lambda. What is So lambda is going to become A. So this becomes A here. Now if you observe, this A is a matrix. These are the numbers. Numbers multiplied with a matrix will give you a matrix. You know that basics. Now this is the number. Can number plus matrix will give you same matrix? No. So that is the reason we need to add here, or rather we need to multiply here I, such that now this term is converted into a matrix. So this is the matrix. This complete is a matrix. You please add them and you will get the solution. So now let us do that. So if I just put it this way, that yes, it is 2 into e to the power minus t minus e to the power minus 2t into I. What is I? I is nothing but identity matrix. What is that? 1 0 0 1 plus what do we have is this one. What is that? E to the power minus t minus e to the power minus 2t into what? Yes, A. What is A? What is A? A is given over here. A is nothing but this one. 0 1 minus 2 minus 3. 0 1 minus 2 minus 3. If you see, this is the same problem which we have done in case of inverse Laplace transform, right? It is the same problem. Why we took the same problem, such that we will understand that we have at the end we have the same solution as of the inverse Laplace transform method, right? So now yes, let us simply do this. So what you get here? Yeah, yes, you get 2 into e to the power minus t minus e to the power minus 2t, and this one multiplied with this 0 will give you 0 here, and then again this multiplied with this 0 will give you 0 here, and this one multiplied by this one, you get 2 into e to the power minus t minus e to the power minus 2t. So this is the thing, plus you just simply multiply this. If you multiply this with 0, you get 0 here, right? Then if you multiply this with 1, you get the same expression e to the power minus t minus e to the power minus 2t, right? If you multiply this one with this minus 2, what do you get here is minus 2 times e to the power minus t minus 2 times e to the power minus 2t, right? And this particular one here you have minus 3, right? So this becomes minus 3 into e to the power minus t plus 3 times e to the power minus 2t. Now you please simply add these one consecutively. After adding them, what you get is these terms consecutively, you just add them. So after adding them, what we get at the end is e to the power at is equal to 2 times e to the power minus t minus e to the power minus 2t e to the power minus t. So yes, this is the expression that is you have got. This is nothing but the state transition matrix e to the power at, right? So this is the whole concept, right? Now if you see, we have got the same expression in inverse Laplace transform approach as well, because everything was same, matrix was same, but yes, we are trying to find the STM by two different ways. Then yes, definitely the solution has to be same, right? Now let us take another case of such things in the sense I will tell you. Now if you see, we have applied the Cayley-Hamilton theorem when the eigenvalues are distinct. See, do you see here? Eigenvalues are distinct, right? Lambda 1 is minus 1, lambda 2 is minus 2, right? Now we will take such a case wherein eigenvalues are repeated. Because what will happen there, just try to understand. See, focus here. The moment, for example, if let us say lambda 1 was minus 1 and lambda 2 was also minus 1, right? So in such a case, if you see, how will you get two equations like this? You cannot get. Why? Because you have one value only. No, you will either put lambda equal to minus 1 only. Yes, so you will get only one equation. How to find the second equation? For that, let us take example. Let us take one example. Yes, so now if we see our step one is what? We need to find the same STM only, right? Step 1 is what? To find eigenvalues. How to find those eigenvalues? Very simple, very easy. Just yes, Si minus A determinant is nothing but 0. How to find Si minus A here? Yes, Si minus A is nothing but what? Yes, you have this S0 0 S, right? Minus, what is A? A is going to be 0, 1, -1, -2, and determinant of this, which is equal to 0. So now if you think of this, becomes S minus 1, 1, S plus 2, which is equal to 0. Is that correct? Now please try to do the next thing. See, now let me find the determinant of this one, because this is Si minus A and that determinant equated to 0, right? So let me find the determinant. How to find the determinant here? Yes, to find determinant means this multiplied by this minus this multiplied by this, cross multiplication, right? So what we have here is S into S plus 2, right? Minus of -1 into 1, right? This is equal to 0. Now the equation that you get is S squared plus 2S plus 1 equal to 0. Now if you think of here, this is 1, let us take this one outside here. Now you need to find two numbers such a way that their addition is equal to 2 and their multiplication is equal to 1. So you will get, definitely you will get 1 and 1, right? The moment you get, because see, 1 into 1 is going to be 1 and 1 plus 1 is going to be 2. So 1 and 1 are the factors. So if 1 and 1 are the factors, which means I have to replace it as S plus 1 into S plus 1 equal to 0, which means S equal to -1 and S equal to -1. So these are the two roots, and these are the two roots which are repeated. Now we know that roots of the characteristic equation, also called as poles, also called as eigenvalues. So let me just say that it is lambda 1 equal to -1 and lambda 2 also means same only, which is nothing but -1 only, right? Now let us try to do the steps. Step 2. What was step 2? What was step 2? Step 2 said that, yes, step 2, right? Step 2 said that you have to express it in terms of e to the power lambda t equal to alpha 1 into lambda, right? Now let us do our normal procedure what we had followed earlier. So let me put lambda equal to -1, because value of lambda is -1 only. See, even if you put lambda equal to -1 twice or thrice or 4 times, you will get only one equation, because you have to find from this particular equation only, right? Anyway, let us try to put lambda equal to -1. The moment I put it lambda equal to -1, I get e to the power minus t is equal to alpha naught plus alpha 1 into -1. Therefore I get e to the power minus t is equal to, what do we say, get here, alpha naught minus alpha 1. This is alpha 1, right? So this is the equation. Let me call this as equation 1. By the way, this was our equation 1, so let me call this as equation 2. There is no problem, right? Now the next step is very, very important. How to find the second equation? Because you have two unknowns here, right? Alpha naught and alpha 1. These are the two unknowns, and the equation that you have is only one equation, right? So you have only one equation here, and you are, by the way, this become big, right? Let me erase it. Yes. Now you have got two unknowns, but you have only one equation. So how to find the second equation? Let us see. To find the second equation, what will I do? Is simple procedure. Differentiate equation 1. Differentiate equation 1 with respect to lambda. How to differentiate? See, d by d lambda. Let me write it on d by d lambda here also, plus d by d lambda. Now, what is there inside? E to the power lambda t. Here alpha naught into here alpha 1 into lambda. That is what is there. Now, if you just apply this d by d lambda into e to the power lambda t, which is nothing but, yes, derivative of e to the power lambda t with respect to lambda, means lambda is the variable. Lambda is the variable, right? Now if you see here this particular derivative, because see, it is not just e to the power x, right? Because we know that d by dx of e to the power x is nothing but e to the power x. Let me just write it down somewhere. D by dx of e raised to x is nothing but e raised to x, right? That is what we have seen. But what about if you have e to the power lambda x, or let me say that if you have this 2x here, for example. So if you have e to the power 2x, then in such a case what we do is we just assume this whole term as x and make it as e raised to x. Try to find the value, yes, e to the power x only. So in place of x you are going to write 2x. Similarly here, if you see, it is going to be e to the power lambda t multiplied by definitely derivative of d by d into d lambda of whatever you took as lambda. So it becomes derivative of this one. Is that correct? Yes. Now next if you see, it is going to be d by d lambda of alpha naught. What is alpha naught? Alpha naught is just a constant, and we know that derivative of a constant is going to be 0. Now plus d by d lambda of what? Alpha 1 into lambda. Just take alpha 1 outside, it is a constant, multiplied by lambda. So it becomes d by d lambda of lambda, d by d lambda of lambda. What is that? It is going to be 1, because we know that, for example, if it is dx by dx means derivative of x with respect to x, then it is equal to 1. Similarly, it is nothing but derivative of lambda with respect to lambda, so it is also going to be 1. So from here, if you see, the equation that you get is e to the power lambda t. What is d by d lambda of lambda t? T is a constant, take it out, that's it, and d by d lambda is going to be 1. So you get t, you get it as t into e to the power lambda t, right? T into e to the power lambda t, which is nothing but equal to alpha 1. This is alpha 1. So if you just see here, you have already, so yes, this is the expression for t into e to the power lambda t, which is equal to alpha 1. Now let us replace, let us put lambda equal to -1, because this is the another equation that you have got. This is nothing but the equation 3 that you wanted. Now you have got these two equations, right? Now let us put here lambda equal to -1. So if I put here, what do I get here? Yes, if I put lambda equal to -1, what do I find? Find that it is t into e to the power minus t, it is equal to alpha 1. Do you have the value of alpha 1 here? Let me call this as equation 4. Yes, alpha 1 is present. What do you want? You want alpha naught. How to find alpha naught? Just simply put 4 in equation 2. This is equation 4, this is equation 2. If you replace this alpha 1 here, then you will definitely get the alpha naught. So how to get that? Yes, put 4 into. So if I put 4 into, I get e to the power minus t is equal to lambda naught is there, right? So lambda naught is something that I want, minus alpha naught is there, which is, yes, taken here, right? Similarly, after that I am going to have alpha 1. So if it is alpha 1, what does that mean? What is alpha 1 equal to? Alpha 1 equal to t into e to the power minus t. So it becomes minus t into e to the power minus t. Is that correct? So now how to find alpha naught here? Alpha naught is going to be e to the power minus t plus t into e to the power minus t. I just took this one on the LHS. So this is what is the expression we have got. This is the alpha naught. Getting my point, right? So now since we have the alpha naught values as well as alpha 1 values, it is very simple now, right? So yes, so now what will I do is, I will simply replace this 4 and this 5. Let me call this as equation 5. I will just simply replace this 4 and 5 in this equation 1. So put 4 and 5 in equation 1. By the way, understand the concept. If the poles are repeated or if the eigenvalues are repeated, in such a case the second equation is formed by taking the differentiation of the first equation. That is very important, right? Anyways, so now if you just see here, what do you get? Yes, e to the power lambda t, you have to replace it here, right? E to the power lambda t equal to alpha naught plus alpha 1 into lambda. So it becomes e to the power lambda t plus alpha naught. What is alpha naught? Alpha naught is this one. So it becomes e to the power minus t plus t into e to the power minus t. E to the power minus t plus t times e to the power minus t. Right? Yes, definitely. Now what is next? Plus, yes, we are going to have alpha 1 into lambda. What is alpha 1? Alpha 1 is nothing but t into e to the power minus t. From equation 4 we have got. So t into e to the power minus t, that is what we have got, into lambda. Is that okay? Yes. Now if you see here, this lambda which is there, lambda is a number. Why? Because it is eigenvalue only. No, basically it's a number. So it is fine till now. Now what are we supposed to do? We are supposed to apply the Cayley-Hamilton theorem. The theorem says that every square matrix satisfies its own characteristic equation. So if this is the characteristic equation, then is definitely it has to satisfy. So yes, it is going to be what? So I can just simply replace this lambda by a. That is what is the concept, right? So if you see, this becomes e to the power lambda t e to the power a t, which is equal to e to the power minus t plus t into e to the power minus t, plus if you think of it, becomes t into e to the power minus t into e to the power minus t into a. Now you please note here, since this is matrix A, matrix multiplied by number gives you a matrix again, but this is a number, so number plus matrix does not give you a matrix. So yes, definitely you need to convert this into a matrix. So in order to convert it into a matrix, I am going to write here I, right? And yes, e to the power 80 is there as it is. So the next step that we have is e to the power 80. Now see, since it is multiplied with I, what is I? What is I? I is nothing but identity matrix, right? So if it is identity matrix, see, rather wait, let me just do it another way. Let me just take those things simple. Yes, if I have e to the power minus t plus t into e to the power minus t, right, multiplied by this I, what is I is going to be 1001, right, plus yes, again it is t into e to the power minus t, it is the constant or it is the number, multiplied by this a. What is matrix A? Matrix A is given as 0 1 minus 1 minus 2. Is that correct? So 0 1 minus 1 minus 2, that is what is given. Perfect. Now you please see here, this is equal to what? Yes, it is going to be equal to, yes, this one multiplied by this one, you get same e to the power minus t plus t into e to the power minus t. Similarly, this one multiplied with 0 gives you 0, this multiplied with 0 gives you 0, and multiplied with 1 you get e to the power minus t plus t into e to the power minus t, right? Now plus what we have is t into e to the power minus t, so it just becomes this into 0 is 0, then you have this t into e to the power minus t here, then since it is multiplied with minus 1, so it becomes minus t into e to the power minus t, and you have this minus 2, so it becomes minus 2 into t into e to the power minus t. If you add them at the end, what you get is e to the power 80 is equal to, so yes, at the end you get the state transition matrix as e to the power minus t plus t into e to the power minus t. Second element is t into e to the power minus t. Third element is minus t into e to the power minus t. And the fourth element is e to the power minus t minus t into e to the power minus t. This is nothing but the state transition matrix e raised to at. After that, if you are interested in the solution, you can do the simple thing. Yes, you know that y is equal to c into x, c into x, right? C into x of t. Now, if you see here, this is e to the power 80, right? So to find x of t, you know that it is nothing but x naught into e to the power 80, x naught into e to the power 80. You please find this x of t, and then whatever value you get of x of t, you please replace it here, multiplied with this t, you are going to get this y. So solution can be easily found out. Yes, so now we have seen about how to find the state transition matrix, how to find the solution by using a Cayley-Hamilton theorem approach. Thank you.